Let's take a look at what appears to be a fairly complex problem and see how we can simplify it and make it easier to analyze. So what we've done is we've taken this printed circuit board, PC board, and we've drawn the schematic diagram for that circuit board. And you can see when you compare the board to the schematic diagram, it's pretty much drawn to the exact relationship of the components of the resistors. The next thing that the author did here was they started rearranging some of the relationships and the placement of the components on the board to try to make them easier to do the series parallel analysis. So in the figure, the schematic is drawn in the same arrangement as that of the resistors on the board. In drawing number B, the resistors are rearranged so that the series parallel relationships are more obvious. So you can see they brought down R3, they pulled it out and brought it down, and they showed clearly what the parallel relationship was between R5 and R6. R2 stayed where it was, R1 and R4 stayed where it was, and they merely then dropped R7 down into the series relationship that it holds. So in the drawing, then you can see R1 and R4 are in series. R1 plus R4 is in parallel with R2. R5 and R6 are in parallel, and this combination is in series with R3. So we can see that whole arrangement. R3, 5, and 6 series parallel combination then is in parallel with both R2 and the R1 R4 relationship. So we can see that how this is laid out in these blue boxes by the explanation. This entire series parallel combination is in series then with R7. So we can write the shorthand detail for the RAB, which it would be the equivalent or total looking into port AB, as R5 in parallel with R6 plus R3 in parallel with R2. Okay, so we can see that right over here. And then R2 is in parallel with R1 and R4. We see that over here. And everything else then is in series with R7. So by doing that, we've simplified the look and functionality of the PC board as it relates to a schematic diagram that's more easy to analyze. Okay, so we're going to take a look at continuing the analysis, determining total resistance from the analysis, looking at how we can determine currents and voltages. So if you know Ohm's law, Kirchhoff's law, the voltage divider law, and the current divider law, and if you know how to apply these laws, you can solve most resistive circuit analysis problems. So this is everything that we've learned to date. So you should know how to do these. If you don't, go back to the previous chapters and review those fundamentals so that you do have a grasp of how to do this. The ability to recognize series parallel combinations then is, of course, essential. So in determining total resistance, you learned how to determine total resistance in previous chapters. In 6, you learned how to determine total parallel resistance. So to find the total resistance, R sub T, of a series parallel combination, you simply define the series parallel relationships, then perform the calculations that you've previously learned. Okay, so to find the total resistance, R sub T, in a series parallel combination, simplify, define the series and parallel relationships. Okay, so in this example, fairly simple example, we've got 3 resistors. R1 in series with the parallel branch R2 and R3. We've got a 10 ohm and 2 100 ohm resistors. So first, we calculate the equivalent parallel resistance of R2 and R3. And generally, that's the way we go about solving these types of problems. Look for the parallel branches that you can simplify and turn into either another parallel branch that can be used to do the analysis, or where it can be then made into an equivalent and put in series. So R2 and R3, will become an equivalent relationship for a 50 ohm resistor that will be in series with R1, the 10 ohm. So when we calculate the equivalent parallel resistance of R2 and R3, we can see then that R, we're going to use the simplified relationship, R over the number of resistors in the circuit. In this case, there's only 2. Smaller than the smallest, we get 100 divided by 2, or 50 ohms. So notice here the term R2 in parallel with R3 is used here to designate the total resistance of a portion of the circuit in order to distinguish it from the total resistance R total of the complete circuit. So now that we have the 50 ohm equivalent here, R2 in parallel with R3, it's just a matter of summing R1 and R2, together, and we get a total equivalent resistance of 60 ohms. Okay, so let's take another example. Determine the total resistance between positive and negative terminals of a battery. So in this case, you notice that they've got it drawn with 2 grounds. All that means is that this point ground are together. We could draw a line straight across here and achieve the same relationship. So the thing that you should do when you see a circuit like this is start keying in on where do I have parallels. Well, I can see right there I've got a parallel. That's going to turn into a resistance. That's going to become a parallel branch by itself in parallel with this branch. And then all of this from A to B will merely sum to R1. So you will learn to look at that and pull those relationships out fairly quickly. So in the upper branch, R2 is in series with R3. This series combination is designated as R2 plus R3 and is equal to R2 plus R3. So we sum those together and we get 47 ohms plus 47 ohms gives us 94 ohms. So now we have our relationship on the top here of 94. The lower branch, R4 and R5, let's go back here. So here's R4 and here's R5. R4 and R5 are in parallel with each other. Okay, so let's look at it. So you can see there, those are in parallel, these are in series. Are in parallel with each other. This parallel combination then is defined as R4 in parallel with 5. So we use our relationship, the product over the sum. So R4, R5, R4 plus R5, sum, or product, sum, divide, we get 24.8 ohms total. So that forms the branch, each of these branch resistor relationships. So now we have this in parallel with this. So also in the lower branch, the parallel of R4 and R5 is in series with R6. Let's go back. So there's R6, R4 and R5 in series with R6. So I take 24.7, I add it to the value there of 75, and I get 99.8 ohms. So I've simplified the top branch and the bottom branch into those two values. So now I need to determine what the parallel equivalent is for 94 ohms and 99.8 ohms. Okay, so in doing that, and I don't have that relationship here, I'm going to take the product over the sum, I'm going to come up with that value, and I'm going to add it to 100 ohms. Okay. Once you know the total resistance and the source voltage, you can find the total current in a circuit by applying Ohm's law. So we're just going to use these totals and source values. So if I had a source value of 30 volts and a total resistance of 148.4 ohms, I would have a total current then of 202 milliamps. By using the current divider formula, Kirchhoff's law, Ohm's law, or the combination of the three, I can find then the current in any branch of a series parallel circuit. So in this example, again, fairly simple example, we've got 2 resistors in parallel, 1 resistor in series. So the first thing I'm going to do is I'm going to tackle the parallel branch, R2 and R3, and I'm going to sum it with R1. So the total resistance in R1 added to the product over the sum is equal to 1 k ohm plus the product over the sum is equal to 2.32 k ohms is the total resistance or total equivalent resistance for this circuit. Since I know 22 volts is the source voltage and now 2.32 k ohms is the total resistance, I can solve for the total current and I get 9.48 milliamps. So now I can use the current divider rule for two branches to determine the current through R2. So there's there's R2. I want to know the current there. So I'm going to use the current divider rule. So in this case, R3, which is the opposite resistor, divided by the sum of R2 and R3 times the total current, which gives me 3.3 k ohms, divided by 5.5 k ohms, times my current that I just solved for, 9.48 milliamps, and the current through R2 solves out to be 5.69 milliamps. So I'm going to do the same thing. I can do the same thing in the other side here, or I can just use Kirchhoff's current law. The easiest way to do it is Kirchhoff's current law. The total current is I2 plus I3. So if I solve for I3, then I get I total minus I2 is equal to 9.48 minus 5.69 milliamps, and I get 3.79 milliamps of current through that resistor. So you can see you don't have to use the current law, the current divider rule. You can switch to one of the easier ones if Kirchhoff's current law makes it easier to solve for the relationship. Okay, so before we move on to our next little example here, let's go ahead and stop and take a breath.